unless you're working in exactly what they're interested in, then you have to go with the other sources. Inflation has eaten that up pretty much. And I talk to my other colleagues, we all say, how can this go on? This is not possible. It's not sustainable.
If you have unlimited resources in terms of, let's say, funding, what project would you pursue right now?
Oh, I have a lot of things I'd like to do that I can't do. I would go back. So I had to sort of abandon is a strong word because I don't want to abandon it, but stop my research on bioimaging in the lab, right? After COVID, during COVID, I would take that up again and, really boost that and have a much bigger group working on bioimaging. Because I think that there's a big role for iron oxide nanoparticles as MRI contrast agents. It just needs time and money to get it to work. And I have neither. Well, I don't have the money and I don't have the students.
Students are the rate limiting factor?
Well, no, the paying the students. All comes down to money.
Yes.
What's the fundamental need for contrast in MRI, and also what are the kind of different solutions that are possible? So what would be the unlock of having it work?
So MRI contrast actually works really well. If you have an injury, like a joint injury or something, you probably will get contrast. Contrast agents today are all based on gadolinium. It works really well, and the radiologists love it. You see a bright spot where you have more gadolinium than when you don't have gadolinium. You can see, all these things. But gadolinium is not a natural element that you find in the body. The early gadolinium contrast agents caused a condition called, NSF. It's kind of fibrosis, basically a lethal thing with very small fraction of patients ended up with this condition. And it turned out that was related to their kidney function. So if you had bad kidney function, you were much more likely to get this condition. So there was a black box warning from the FDA. So people with, kidney disease couldn't get contrast. That's been fixed to some extent, but there's still an issue with the nephrologists who don't want their patients to get a lot of gadolinium. And more recently, in the last 10 years, it's been realized that gadolinium also seems to be found in the brains of patients that have multiple contrast injections, like multiple sclerosis patients that need to be imaged often. Their brain glows. You take an MRI of the brain and there's all this gadolinium in there. What does that do? We don't know. So right now it seems to be benign, but gadolinium is not that cheap either. And if you want to do targeted imaging, so right now contrast agents are not targeted. They're largely blood pool agents. They go where water is. But you want targeted agents, targeting, let's say, collagen or something like this. You're going to need a lot more quantity of these agents. You're going to have to inject more material than you do for blood pool agents. So the toxicity problems will go up and the cost will go up. You can make really tiny iron oxide particles to mimic the properties of gadolinium. This is something that we discovered with our collaborators, Alvin Jasanoff, for instance, here at MIT in bioengineering. Iron is not gadolinium. Iron is already in the body. There's already a lot of knowledge about iron oxide, and it's fairly benign. And if it's small enough, it gets excreted in the kidneys very quickly. It's not a problem. And if it doesn't, it goes to the liver. But the liver is full of iron, especially for pediatric patients. You don't want pediatric patients that need to be imaged often because of whatever illness they might have. You'd really like not to use gadolinium. And also from an environmental perspective, it turns out to be an issue. San Francisco Bay, Boston Harbor, Tokyo Bay, they have a much higher level of gadolinium than the ocean should have, right? And so there are fish there, and they drink and eat and all these stuff, and they end up with more gadolinium than you'd like. The Japanese are much more worried about this than the Americans, apparently. Because I go to Japan and they're worried about this. And I talk to radiologists here and they say, oh yeah, there's no problem. We love gadolinium. We know how to read the images. It's great stuff. Why would I want to change? So, there's this tension. But I think in order to convince people that iron oxide is a viable replacement, you need to work on it. You need to spend the time to do the animal experiments, the chemistry. It's going to take time and money. And I'd like to work on that.
It does sound like something the NIH would fund. Like this sounds
but NIH
really great.
NIH has become an agency that reimburses research. It doesn't fund proposals. It reimburses what you've done. You write a proposal, you have all these preliminary results, You've already done a lot of the research, and then you get
true.
your money.
What is your current funding mix like? Do you have a lot of funding from companies, from the private sector, or is
Yeah,
it?
that's a really great question. So I would say my funding comes more and more from private companies. And the reason for that is the cost of research, it just keeps going up. It goes up faster than inflation in some cases, and especially the last 5 years, it's really gone up. As the primary cost of research here at MIT is the cost of students, salaries and equipment. But really day-to-day, it's salaries. That has accelerated in the last 5 years. Postdoc salaries have gone up a lot, and graduate student cost of living in Boston is expensive, right? When I started at MIT, you could run a reasonably large group, reasonable group with 2 NSF grants. Now an NSF grant, if you're lucky, pays for 1 graduate student.
Yes.
And then no equipment, forget about equipment. And the success rate is much lower today than it was back then. And then you have to have done the work already, pretty much. You have to have a lot of preliminary results
Yes.
to convince referees, because the referees are so conservative. They'll find ways to tell you that it's not going to work unless you show them that it's going to work already before you get the money. So there is a crisis of funding from NSF and other federal agencies for fundamental research. Targeted funding from agencies is still okay. Very specific funding for very specific things. Congress will allocate, a set amount of money, and suddenly you have all this money available for something very specific. But unless you're working in exactly what they're interested in, then you have to go with the other sources. Inflation has eaten that up pretty much. And I talk to my other colleagues, we all say, how can this go on? This is not possible. It's not sustainable.
Wow.
1 graduate student on 1 grant, now maybe 3/4 of a graduate student, how do you pay for the other quarter? You get half a postdoc. How do you pay for the other half of the postdoc?
Yes.
You
Yes.
can't divide
Yes.
people in two. You can't divide people in two,
No. Yeah.
right? But you're still expected to write a proposal that proposes to do as much as 20 years ago, but with 5 times less resources. It just doesn't work. It doesn't work anymore. And at some point, when you get to, instead of 3/4 of a student, it pays for 1/4 of a student, this just doesn't work. We have to rethink how we fund science, right? Especially at MIT, I think, because when we look at our competing universities, the cost of research at MIT is particularly high because we don't have a lot of graduate student fellowships. So you look at Stanford, they've built up a huge war chest of endowed graduate student fellowships. Princeton Chemistry subsidizes all the chemistry graduate students for the first 3 years. It's a huge, huge deal, right? So then they only pay for materials and supplies from a grant as opposed to paying for. Then you can run the same project with a lot more students than I run with 3/4 of a student. How can I compete? The companies will still pay for the cost of doing research. So if I go to a company, I say, I need 2 postdocs, and they'll agree, okay, you need 2 postdocs to do this. And I say, each postdoc costs blah. They say, okay, and then they pay you blah, right?
Yeah.
They don't try to tell you, okay, the only thing I'm going to give you is, if you go to NSF, they tell you, I'm going to give you $150,000, and it doesn't matter what you propose, I'm
Yes.
going to give you $150,000.
Yeah, I hope postdocs and grad students would appreciate to hear that, how many efforts it takes from the faculty to secure this 1/4 of a student, and they need to basically pick it up
Yes.
from several grants, and you
Yes.
have that special opportunity to work here.
And places
then-
like MIT take a high overhead as well.
I'm
Yeah.
really shocked to hear that from one of the most established professors at one of the most established places like MIT. It's like what others are doing and surviving in the field of academical science and research.
Yeah.
Do you think that a place like, we talked about Bell Labs and how it's literally the opposite of this story, right? Like you walk down the hall, talk to one person, and basically they understand you and fund your project. Is there a place like that exists at this point for the kind of fundamental work that a lot of people get into science for, right? And if it doesn't exist, is there a possibility of recreating it? Like
That's a great question.
I think that's
Bell
something
Labs
that-
no longer exist. So places like Bell Labs really no longer exist. But Bell Labs was an anachronism of the fact that AT&T was a monopoly, which had a lot of problems. AT&T being a monopoly basically killed innovation in communication for so many decades. After AT&T was broken up in the 1990s, that was a revolution in communication. You know, the cell phones came out.
Yeah.
Yes.
When AT&T was a monopoly, you couldn't buy a telephone. You had to rent a telephone from AT&T. And everybody had the same phone, and the phone didn't change for 30 years because there was no motivation to make a better phone. That was terrible. But at the same time, it was a monopoly, so it could fund places like Bell Labs. And it didn't really care what Bell Labs did because its money came from running the long distance network as a regulated monopoly. And it really didn't know what to do with what Bell Labs did. It was the cost of being a monopoly. The cost of being a monopoly for AT&T was to run Bell Labs. And they were, okay, fine, you know, we make all this money anyway, so we just put a little bit of it as a tax to run Bell Labs. As long as you were doing something that could be tied in some way to communication, you know, you could do whatever you wanted at Bell Labs, as long as it was interesting. And that's why it went away.
Yeah, I mean, you wonder, you know, who's actually in this position now. It's maybe companies like Google, right?
Yeah, no, but Google isn't Bell Labs. Google is not a monopoly.
Yeah.
Google is driven by short-term profit. Google X, you know, all these things that they're very focused on something that can become commercial in the 3 to 5 year range or sooner. They're not into long-term basic research.
And the same in universities. Like, I feel like the topics move so fast. Like what I have done during my PhD, it doesn't matter maybe right now. And I think it depends on the grants, so that the fields move pretty fast, like not with the pace as it was back in 80s, or when you have quite a lot of time to go deeper into the problem and find a solution for that.
There's a lot of interesting science that's being done in biotech startups because there's a feeling there that still there's some fundamental things that, but it's still motivated by particular things as opposed to just curiosity driven. It used to be, you know, when NSF actually funded research at a much higher level within the groups, that you could have enough resources to spend some of your time on stuff that was really just curiosity driven, because there wasn't, if there's enough money around, then you can spend some of that on stuff that you don't know where it's going to go. But when the money becomes restricted and you want to be able to renew your grant, you got to write papers. You got to have an output that's based on what you wrote in your proposal. It doesn't allow you to go sideways and, you know, you discover something interesting. How do you fund that now?
Yeah, this is a discussion that I feel like comes up in so many different contexts, like even with people that I know. So I'm no longer in academia. I work at a startup also that I co-founded, and just people that I meet that never even went into academia for fear of this issue, right? That they're worried that, you know, they'll kind of this magic of working on something that's more curiosity driven has been eroded out of the system. And it kind of, you can think about it two ways, like either maybe we're in a period where this is at a low and maybe the curiosity driven funding and things like that will return, or maybe the opposite is the case, that we've evolved to a point where like maybe science is saturated and like curiosity driven stuff is no longer considered important because maybe it's less fruitful, like empirically, you know. I don't know, it's kind of, I mean, you know, like we haven't
I'm going to push back on that.
You mean like diminishing returns?
Well, like for example, you know, we haven't had like, okay, has there been like a physics driven product, for example, that's been released in the last, I don't know, 50 years, for example, like versus, you know, applied physics or whatever, you know, we haven't had a lot of new physics, you know, driving maybe since radiation. I don't know. I
mean, the last 50
years. Yeah, the
years.
laser, so. I guess. I don't know. It's like the laser is already pretty applied, right? So, but anyway, I'm just saying that it could be that
the quantum well lasers that were developed in the 1980s. That's
quantum
less than 50 years
lasers.
ago.
Yeah.
They're a multi-billion, trillion-dollar business. They're the root of communications today.
For sure, but I wonder if the kind of or at least I'm not arguing for this. Like I would love it. This is why I asked the question. Yes. But I wonder if the kind of like hard-nosed response to this would be that, okay, the way we make a quantum well laser is we give you like super focused funding. We already know what we want. You know, we want to bet whatever, right? Yeah. Like this kind of thing. Maybe the idea is that model is actually working well, and like, you know, MIT and all these other places are producing a lot of amazing research in these like very constrained kind of like applications focused. I would argue that not, in my opinion. I think actually what's happening is people are getting better at selling the results. Like, you know, the headlines look good, but they're not, the substance has not improved from like focusing it on applications. But maybe because people have optimized the optics, it looks like, oh, if we focus on applications, we get more results, right? But I think there might be like from the perspective of people doing the funding or something? I have no idea. I mean, we should actually interview somebody that's on the other side of this, right?
It's
Yes.
the perspective of Congress.
But
Congress holds the purse strings.
But yeah, it could be that kind of by focusing on applications and all these, and kind of like forcing that from like the forcing function being, okay, we're going to tie funding to results and applications and actually results that you already have, right? Versus, which is, I think, one of the funniest thing you said in the interview is that, NIH is reimbursing for research, which is kind of the feeling I've also had. We've applied for one NIH grant at the company where I work, and it felt like you basically had to have it finished before applying. Maybe that the people who kind of have driven these decisions would argue that, oh, look at all these amazing results it's creating. Now we have XYZ, all these startups coming out of academia and all these things. So I don't know. I wonder if this kind of motivates a future interview, I think, with somebody that's on the other side of the table.
Yeah.
But it's hard not to empathize with what you're saying. Like it sounds extremely rational.
The average time between invention and Nobel Prize in chemistry is 30 years. That's what it was for me. And the internet age has really not changed how long it takes to go from a curiosity-driven discovery to a commercial application. It's going to be 2 or 3 decades. Let's wait 30 years from now and see what we've killed. But we won't even know.
Yeah,
we won't even know.
That's the crazy thing.
We won't know. We just won't know what we're missing.
What if you hadn't worked on quantum dots? What area would you like? What's the road that you didn't take but you sometimes fantasize about? Like what would be the other area that you would have been excited to work in?
Well, I wanted to work in ultrafast spectroscopy. That was kind of new at the time, really, to use ultrafast lasers to understand the kinetics of mechanisms, at the femtopicosecond timescale.
Oh, attoseconds. You could have won a Nobel Prize in attoseconds.
Attoseconds, yeah. But I didn't.
And outside of science, have you ever thought about when you were a teenager pursuing a different career, or was it very clear that it would be science?
I was a violinist from a young age. Music would have been something that I might have considered ever so briefly when I was younger, but otherwise it would have been science.
Is there anything from your side which you would like to add or, I don't know, tell especially younger generations of scientists, engineers, chemists?
Even with all the challenges of funding that we talk about, it's still fun to be a scientist. I wouldn't trade it for anything. And you find your way. I mean, foundations are a way to get money these days. So the funding model may evolve. It's evolving. You find a way. Universities are going to find a way. There's enough money in universities. It's a question of priority. If it becomes clear that the priorities are just wrong, the equilibrium will come back. And you can see that like at Princeton or Stanford, where, they're willing to pay for graduate students, which is their biggest source of cost.
A follow-up question to that is, if you're somebody who's already in the lab and kind of maybe in a grad student or postdoc role or early professorship, how do you make sure that when something comes, like an accident, like a happy accident happens, how do you make sure to grasp it, right? Like what's the kind of how do you position yourself towards your research so that you can be the beneficiary of basically the
luck?
Just a search space, right? You're doing a search across some multidimensional space, and like how do you make sure that you don't miss the inevitable things that you'll find?
Curiosity, when something happens and it's not what you expect, why? Just don't dismiss it as being a pathology that's of no interest. Most of these discoveries are from effects that you don't expect. So if you see something that you don't expect, and it might be interesting, so pursue it. Just think about it a little bit. I often wonder how much. So when I was first an assistant professor and I was actually in the lab looking at data come out, I saw things that my students thought were artifacts or were not what they expected. And I saw them and I thought, this is a gold mine. And that comes with curiosity and experience, but mostly curiosity.